The last valve type we're going to look at is directional control valve. So we've already talked about how to control pressure in a circuit, how to control the flow rate in a circuit. The directional control valves tell us where it's going to go. So it sends it to one part of the circuit or another and allow it to flow one direction or another. So they're in some ways a little bit more simplistic, but in some ways they can be more complicated depending on how complicated our control needs to be. So let's take a look at some directional control valves, and we'll look at the simplest one. The simplest one we can look at is a check valve. And the symbol is very simple, and again, like all the symbols, is very descriptive of what it looks like or how it would function. So let me get my pen up here. So we basically show a ball in line with a angled seat, and it's like that. So in this particular case, the way I've drawn the symbol there, if the flow tried to come from the right, it would push that ball into the seat and would not allow the fluid to flow through there. If it flows from the left, it will lift the ball off the seat, flow around the ball, and move on. So, and they are basically that simple in construction. So there is a concept of one in the upper right over there that shows sometimes we have a light spring in there to keep that ball seated to make sure that the fluid doesn't sneak around it. But again, in this particular case, flow comes from the left, would push the ball away, flow around the ball, and head right out of the outlet port. This is what the cutaway of one more like what an actual construction would be. So it's a little bit more complicated than that. They have different ways to seat the ball in there so they get a good seal so it doesn't wear out and so forth. So it's not always a ball, it's some type of a bullet-shaped thing. The lower left there is what they will actually look like. So, it's an example of one that we would plumb into a system. And notice that they actually, on this manufacturer, actually shows the JIC symbol on the outside of it. And that gives you directionality too. So I can look at that symbol and I know that in this particular valve, the flow would be free flowing from left to right, but from right to left it would be blocked. And so that tells me what goes on with the check valve. So that's the simplest one, is the check valve. As we go at a level more in complexity, we move into what we call spool valves. And here's where we can start building really complicated valves. They can be simple, but they can be pretty complicated too, to do a lot of neat things for us. So let's look closely at this spool valve. You can see the cutaway on the right there of what goes into them. They are complicated. There's a lot of ports. On the left is a concept of how these things would work. So looking at that, the spool in the middle there, so this gray bar going through with the dark lands on it, those are all part of a spool. So you can see the corollary to that spool. The real looking spool is this silver line that goes through the valve body on the right, and you can see that there are lands on here, there are grooves that are machined into there. These are very precisely machined. Usually we don't use a lot of O-rings or other type of seals on here, so we rely on very tight tolerances to get the seal to keep the fluid from leaking around the lands and so forth in those spools. So they have to be pretty tight. But here's how they work. And usually, and this is a common one that we use, where we have 4 ports, although this one shows 5 connections to it, or 5 lines going in and out. But realize that the reservoir, there are 2 reservoirs here, so they would be internally with all these ports that move around inside these valves. Those 2 would be connected together internally, and I would have one external connection that would say reservoir. So look at the pump supply. So the flow coming from the pump would come here. And when this spool is in the neutral position, like it's shown here, we do not allow any of the flow to come from the pump. So the pump would be stopped there, so no flow would go. So I'd have to have a relief valve somewhere to protect that, to dump the system flow to some other place. The outputs down here, we have 2 outputs. We have port A and port B. So they could be connected down here to a hydraulic motor, to a cylinder, to some other type of actuator, whatever. And notice that they are also locked and sealed, so we couldn't have any flow going in because they're sealed. You look at the flow, can't go there. So now this spool to the right. So if I slide this spool to the right, what's going to happen is this land is going to move over to the right. It's going to open up this port. This land will also move to the right, as will this one. So they all move together. So what that says now, hey, the pump supply, when this moves to the right, this is going to open up the passage for the pump supply to come out here. And this land will not quite come over and cover port A, so that's going to be a free-flowing path for the fluid to come from the pump out to port A. And then it would go through the actuator or whatever is connected to it out here, and there's usually a return flow, so whatever goes out comes back. That return flow would come back. This land is moved to the right, so that allows this flow to move back to the reservoir. So what that does is open up the flow, allows it to go out to port A, come back from port B to the reservoir. Likewise, if I slide the spool the other way, the pump supply can go out to B and then come back from A to the reservoir. So now I reverse the direction of flow. So from B to A and back to the reservoir, or originally I can go out of A back to B and back to the reservoir. So that's what's going on. And again, these can be really complicated. And you see this one has multiple functionality here with probably some pressure control and maybe even some other ways to help actuate this valve. So there's a lot going on in there. We can stack multiple of these together. So you see in the lower right is a valve stack. So there's a bunch of ports. Every one of these handles is connected to a spool. They're all stacked together, and this would be nice because I would usually connect the pump supply to one end of this stack. The oil would go through that stack. The return of the reservoir side, of the tank side, is on the other side of the valve stack. And then each one of these pairs of ports on the top would be my A and B for whatever I want to actuate. So I could actuate a number of different systems with that, different actuators and simultaneously and so forth. And we'll talk about what happens if we try to do them simultaneously. So let's look at the JIC symbols for these. Again, they're very, very descriptive. So these are what the JIC symbol would look like. And let me get my pen because what we typically show are the different positions. So as I would put this one in a circuit diagram, I would actually have 4 lines connected to it like this. 2 of these lines, one would be my pump, one would be my tank, and these over here would be my port A and port B. And so that would tell me which way that liquid is flowing, which way I would allow it to flow. So here's my pump supply, and in the neutral condition, so this has 3 different positions. So you can picture this valve sliding to the left, and then these crossed arrows would be connected to it. So I'll draw that over here in the middle. So if I slid the valve to the left, that would mean the ports would be lined up with this block of that directional control valve. So my port would be here, my pump would be there, the tank would be there, A and B would be there. And in this particular position, the flow from the pump would go to B, return flow from A would come back to the tank. Likewise, if I slid the spool to the right, that would line the pump and the tank up to this left block over here. Pump supply would go to A, return from B. So this is graphically or pictorially what was happening in that spool that we looked at just a little bit ago. These are the common valves that we use, and there's 3 different types. You know that the valves are the same on the left and the right blocks. It's the center block that's different, and those are that we actually call that the center. So different kinds of centers. So the valve on the left is what we call an open center valve. So this is an open center. This is what we call a closed center. And this is what we call a tandem center, actually. So look at what happens. So in the open center, a true open centered system, flow can come from the pump and it can freely return to the tank. Ports A and B can freely return to the tank or the pump, so everything is just kind of sitting neutral. So the load could move or it may not move. Flow from the pump can just short circuit right back to the tank, so there should not be much pressure build up against the pump, so it can sit in neutral conditions. Over here, with the closed center, we can see that when it's in the center, flow from the pump can't go anywhere. There's no return to the tank. And likewise, A and B are locked. So whatever the actuator is out here, it can't move either. so we lock everything up. The tandem center is kind of a combination of the two, where we allow the flow from the pump to circulate back to the tank, and that'll protect my pump when I'm in neutral conditions, and it allows the A and the B ports to be locked. Now we can go forever. We can add positions to these valves, we can add ports, and there's just a huge amount of variety that we can do to these valves. Manufacturers make a lot of different kinds, and you can actually special order a lot of different kinds, so you can configure a valve any way you want to. So the options are absolutely endless on what we can do. But a couple terminology things they want us to look at. We have two terms that we use a lot. We call the way and the position. All right. So the way, it's a number. So many way and a so many position valve. So the way is the number of connections that we have to the valve, and the position is the number of positions that the valve can be in. So if you look at these three valves that we've drawn on here already, these are all four-way valves because there's four connections to it, the pump, tank, A and B. So that's a four-way valve, and it's a three position. So there's the center position, the extend position, if you will, and the retract position. So that would be a four-way, three-position valve. Let me draw another one here just to give us an example of what something different might look like. So if I have a block, I'll draw like this. I'm just going to have two blocks in it now instead of three. And I'm going to draw this way, like that. With two ports up there, I'm going to have an A and a B, and I'll call this the pump supply. And this position is going to be over there. All right, so how would we describe that valve? Well, first of all, we look at how many connections there are to the valve. I have a pump and an A and a B, so this one would be a three-way. And then we say, how many different positions can it hold? Well, it can have this position where the flow from the pump is directed directly to port A, or I could slide it to the left so that the pump would be directed through this diagonal arrow to port B. So this one would be then a two position. So that'd be a three-way two position, okay? And we can actually have a four position, and actually these are quite common in agricultural tractors, agricultural equipment, where we'll have an open-centered system, so have what we call a float position on my A and B outlet. So the float position would be something like this, would be the same center that I have here so that the pump is freely going back to the tank. But I would also do the same kind of connection here so that my A and B ports with the cylinder can float, so I can move up and down. And we would do this for a number of reasons, and one good example is if this A and B ports were connected to a hydraulic motor, let's say. So we had a motor that was running a big heavy piece of equipment out there, or some machinery, some big heavy rotating machine, okay? And if we were running this machine in either the retract here, the cross position, or the straight through position, so either turning the motor clockwise or counterclockwise, and we stopped it suddenly and went to the center position, if there's a lot of inertia on this, the mechanical load on that motor is still spinning, it's going to want to try to keep spinning that motor. And if we shut it off, and this is like in electronic circuits, we talk about inductive kick. So if we have a big inductor in there and we shut off the circuit, we get a big high voltage spike and it makes a spark in a switch or something like that. And the same thing can happen here. This big inertia thing tries to keep turning while the motor's trying to keep turning. The motor now becomes a pump, and it tries to shove oil through here, and if I'm in the center position, it tries to shove the fluid back one of these positions. It can't go anywhere. Now I get a real high pressure buildup in one of these lines, and as long as my lines are strong enough, that's okay, but quite often this can be damaging. I can blow a line, I can break a pump, I can blow a seal out of something, so I can have some problems with that. And so that's why when we use the float position then to go from the position where we're operating this load and it's spinning and it's got a lot of inertia, and we take it over to this center position, then now that'll allow it to slow down so the oil can circulate, the motor becomes a pump, and it moves the fluid, but it allows it to move it in this loop, and it slows down gradually and doesn't break something. So that's a float position. So in this particular case, this valve would be still a 4-way valve because I have 4 connections, a pump in the tank and the A and the B, but now it is a 4 position as well, as opposed to these being a 3 position. So that's how we describe valves. We can build them a lot of different ways. The symbology can go crazy with it, so we can actually put symbols on here of how we actuate the things. So that would be a lever that you would see on the previous picture with that valve stack where you had a lever on the end that would move them. We can have push buttons and things like that. We'll put something on the end that will have notches in it like this, and that indicates a detent. So if we have a detent on the valve, that means when we move it from the center to one of the side positions, there will be a lock and it'll stay there. If we don't have a detent, I have to hold it open to make it open. If I leave it go, if I let the lever go, it'll just spring return back to its center position. So we can put detents in there. We can put a symbol like this in there with diagonal lines, and that indicates that it's a solenoid coil. So we'll put electricity in there and we'll activate that with a solenoid. And again, options are endless. We put another one on here with an arrow in the end of it, and that indicates that it is pilot operated. We talk about the pilot operated relief valve. We can actually control spool valves with pressure from another part of a circuit. So when the pressure of another part of a circuit gets big enough, I could actually activate this spool valve. So we can go crazy with it. And again, that's beyond the scope of what we're going to do in terms of design in this course, but at least wanted you to see that. So we will put these directional control valves together. We'll show how we can build some circuits simplistic level and a fairly just to make cylinders track, for instance, or something like that.